When you think about human progress, it's not just about one big invention, right? It's really about learning to build on totally new levels. I'm talking bigger than the tallest skyscraper, smaller than a single cell, and even in worlds made of pure data. Today, we're going to look at how engineering at three completely different scales is tackling some of our biggest problems.
So let's ask the big question. How do we solve impossible problems? I mean, really impossible. Do you build a robot that can help out around the house? Or maybe you design a microscopic machine to cure a disease from the inside out. What about creating an algorithm to manage the entire global economy? Well, the answer, it really just depends on the scale of the problem. And that's the key, right there. It's all about learning to build at every level of reality. We're going to take a journey through three totally different realms. First, the physical world we can all see and touch. Then, the microscopic world we can't. And finally, we'll get into a world that's purely abstract, built from information itself.
All right, so let's start with what we know, right? The human scale. This is our world, the world of things we can actually see and touch. Things like this humanoid robot, which was literally engineered to walk our streets and climb our stairs, right there alongside us.
Okay, that's pretty cool. But what happens when the problem isn't about gears and motors? From here, we're going to take a huge leap, shrinking way, way down, past anything the human eye can see into the microscopic realm, a world where the building blocks are just individual molecules.
And for our final stop, we leave the physical world behind completely. We're going to explore the abstract scale, a universe that's not built from atoms, but from pure information, from data, from algorithms. So, this journey through three incredible scales of innovation, it starts right now.
Okay, first up, the human scale. We're talking about walking robots. And let me tell you, the challenge of building a robot that can walk on two legs, climb stairs, and just navigate a world that was built for people, well, it's a massive undertaking. So think about this for a second. Way back in 1986, Honda's whole mission, it wasn't just to build some clunky walking machine. As they put it in their own research paper, the goal was to create a partner, a robot that could actually coexist and collaborate with us in our own spaces. And this really gets to the heart of the challenge. You see the blueprint on one side and the final robot on the other, but how on earth do you translate the incredibly fluid, almost unconscious way we balance, our joints, our muscles, our sense of gravity, into cold, hard steel, a tangle of wires, and millions of lines of code? It's just a monumental engineering problem.
Okay, so here's why walking is so ridiculously hard for a robot. It's not just one thing, it's this constant, super fast calculation. See, to keep from tipping over, the robot has to use sensors, kind of like our inner ear, to feel when it's off balance. Then, it has to measure the pressure on its feet, what they call the ground reaction force, and instantly adjust its posture and shift its center of gravity. And all of that has to happen before it can even think about taking one stable step. It's a non-stop dance with physics, really.
And the results? They were absolutely remarkable. All this human-scale engineering meant the robot could finally handle the messiness of the real world. We're talking walking on uneven surfaces, squeezing through narrow doorways, stepping right over obstacles, and tackling the ultimate test for any two-legged machine, just climbing a simple flight of stairs.
So mastering the human scale is a huge achievement, no doubt about it. But it brings up a whole new question. What do you do when the problem you're trying to solve is a million times smaller than a robot's footstep? And that brings us to our next stop, the microscopic scale. We're talking about nanomedicine. Here, we're not engineering robots anymore. We're engineering matter itself at the atomic and molecular level to fight diseases from inside our own bodies.
So what is nanotechnology? It's basically the science of the impossibly small. A nanometer is 1/billionth of a meter. To put that in perspective, if a marble were 1 nanometer, the entire Earth would be about 1 meter wide. It's mind-boggling. And we're engineering particles at that tiny, tiny scale to act like microscopic delivery drones for medicine, targeting diseases with absolute pinpoint accuracy.
And here's a crazy thought. While nanomedicine sounds super futuristic, we've kind of been using the concept for centuries. There's a 4th century Roman cup that used gold and silver nanoparticles to change color in the light. But the modern era really kicked off in 1959. The physicist Richard Feynman gave this legendary speech, challenging scientists to start building things at the atomic level, where he said there was plenty of room at the bottom. And that single challenge pretty much gave birth to the entire field we know today.
So how does it actually work? Well, in practice, there are two main strategies. First, there's passive targeting. Here, the nanoparticles are designed to just naturally build up in places with leaky blood vessels, which is common in tumors. But active targeting, that's even smarter. For this, the nanoparticles are coated with molecules that act like a very specific key, one that's designed to fit only the lock on a cancer cell surface. This way, you deliver the medicine directly to the bad guys while leaving the healthy cells completely alone.
All right, so we've gone from the human scale down to the nanoscale. We've engineered robots and molecules, but what if the problem you're trying to solve isn't physical at all? What if it's made of pure information?
And this brings us to our final and maybe most mind-bending level, the abstract scale. We're talking intelligent finance. Here, we're not engineering matter at all. We're engineering information. We're using data, algorithms, and AI to manage these vast, non-physical systems, like the entire global financial market.
You know, the funny thing is, the engineering process in this abstract world looks surprisingly similar to building a robot. You start with your raw material, in this case, collecting just massive amounts of data. Then you process that data to train an AI model. And the final output? It's an intelligent system that can assess risk and, at the end of the day, make critical financial decisions.
And just like with physical engineering, the tools you choose are absolutely critical. A simpler AI model might get you around 75% accuracy, but something more complex, like a neural network, which is designed to learn and improve itself, kind of like a human brain, can push that accuracy all the way up to 90%. So we're not just building simple algorithms, we're building these incredibly smart, abstract machines to manage insane levels of complexity.
But the real power, the real game changer, comes from combining these abstract systems. Think about it. AI brings the predictive intelligence, right? It can spot market trends way before any human could. And then blockchain brings the trust, a secure, unchangeable record of every single transaction. You put those two together, and you can create a financial system that's not only smarter, but also fundamentally more transparent and fair. So we've journeyed through three totally different scales of engineering. We've seen a walking robot, a cancer-fighting nanoparticle, and a risk-assessing algorithm. But what's really fascinating is that when you pull back, you find they all run into surprisingly similar roadblocks. And across all three of these scales, you realize the biggest hurdles aren't really technical, they're human. Take transparency, for example. How do you explain the decision-making of a complex AI? It's often called the black box problem. But that's not so different from the challenge of tracking where every single nanoparticle goes inside the human body, or making sure our robot's actions are always understandable and predictable. No matter what scale you're working at, you face the same basic questions. How does this thing really work, and who's responsible when it goes wrong? And this really reveals the single thread that ties all of this together. Innovation at any scale is never just about the tech. It's about trust. It's about trust in the data that powers the system, trust in the ethics that guide its development, and ultimately, it's about earning public trust in the final creation. Because without that, even the most brilliant piece of engineering is probably destined to fail.
So, from walking robots to molecule-sized medicine to intelligent finance, we've seen how progress is all about learning to engineer reality at entirely new scales. We've learned to build in the world we see, the world we can't see, and in worlds that don't even physically exist. And that leaves us with one final, really exciting question. After all this, what scale will we master next?